Hello and welcome to Physics Teacher. In this video I'm going to go over multiple examples using all the different formulas that are presented in the optics unit for grade 10 science. If you need help locating or how to find images in either curved mirrors or lenses, you can go check out my previous video here. But if you need help with the math, then keep watching because we're going to do that now. Let's get started. Alright, so let's try this question. So one of the first equations we learned is that the index of refraction n is a ratio comparing the speed of light in a vacuum C with the speed of light through a certain material V. So the speed of light in a vacuum C, that's always going to be the same. I think it helps to remember this number. It's 3 times 10 to the 8 meters per second, or 300 million meters per second. That will never change. It's a constant. What will change, though, is V, depending on the material you're in. And since V depends on the material you're in, so does N. So we have a list here of all these different media for all these different index of refractions. Okay, now the index of refraction is a characteristic physical property, so we can use it to identify the substance. So in this first example, we have light moving at 2.20 times 10 to the 8 meters per second through an unknown substance. We can figure out what that index of refraction is, N. So N equals C over V, and that is going to be, so C is 3.00 times 10 to the 8 meters per second divided by 2.20 times 10 to the 8 meters per second. Now, I get a lot of students that have trouble putting this in your calculator, but there's an easy trick, right? 10 to the 8 divided by 10 to the 8 is just 1, so we can cancel that. So in our calculators, we can simply put in 3 divided by 2.2. And that gives us 1.36. We'll round it to 2 decimal places, so 1.36. So part B says to use this table, and we have ethyl alcohol. So that is the substance. All right, let's try another example. Here we find another colorless transparent solid in the ground, and we're trying to identify it. So if we want to identify it, we're going to need to figure out what the index of refraction is. Now what we do in this case, since we can't directly measure the speed of light through it, we shine a ray of light into it at an angle of 50 degrees. So we have air and some unknown substance. And if we have our normal line, which is perpendicular 90 degrees, and we shoot it in at 50 degrees, that's an angle of incidence of 50 degrees, we measure an angle of refraction of 30 degrees. So roughly something like this. What is the substance? Okay, we actually have two values for N. We have air, let's call this N1, and then we have this unknown substance, let's call it N2. So we can use Snell's law here, where Snell's law is N1 sine theta 1 equals N2 sine theta 2, where this would be theta 1, or our incident angle, and this would be theta 2, or our refracted angle. Now for air, N is just 1.00. It's very close to being a vacuum, but to 2 decimal places, we can just have it as 1. Okay, so if this is just 1, then we can kind of just ignore it. So if we rearrange for N2 by dividing both sides by sine theta 2, we get N2 equals sine theta 1 over sine theta 2. Depending upon your class, maybe you wrote it as sine theta I, because that's the incident angle, and sine theta r, because that's the refracted angle. however you write it, it's the same formula. So we're going to put in our angles. So we have sine of 50 degrees over the sine of 30 degrees. When we put this into our calculator, we get 1.53. So what substance is that? We can go back and check our table, and it looks like it is closest to glass, which is 1.52. So the substance is glass. All right, let's move on to another equation. This is called the thin lens equation, and it helps us determine where objects and images are relative to a lens, either converging or diverging. The equation looks like this. My students usually hate this because it's fractions and they hate fractions, but it's not that bad. We'll do some examples with it. But let's go over what the variables mean. So first, dO. That is the distance to the object, and this will always be a positive value. DI, on the other hand, which is the distance to the image, can be positive or negative. If you have a real image, it's positive. And if you have a virtual image, it's negative. So you really need to know the types of images that are produced in lenses, whether it's converging or diverging. So again, if you haven't watched my previous video that helps you find those images in lenses, go take a look at that. And our focal lengths can also be, which is F, positive or negative, depending on whether or not we have a converging or diverging lens. So let's try 3 different examples here. Here's the first example. A camera is focused to take a photo of a bee at a flower. The film in the camera is 11 centimeters from the center of the lens. So what does that mean? Well, if you have your camera, you have light coming off the object, going through the lens, and then will focus on the film. So it's the image that is being focused on the film. So this is the distance to the image. And since that would have to be a real image, since it is being produced on a screen, we know that DI is going to be a positive value. So it is positive 11 centimeters. Then it says the bee is 53 centimeters from the camera. Well, the bee is the object. So this is DO. So DO is 53 centimeters. And the question is, what is the focal length? So we're looking for F. So let's try this. So we've got 1 over F equals, you can switch which side it's on. It's just an equal sign. I like to put what I'm solving for on the left-hand side. That's just a habit of mine. It's 1 over DO plus 1 over DI. Okay, so we can substitute what we know. So DO is 53, so 1 over 53 centimeters plus 1 over DI, which is 11 centimeters. Now these are fractions. You have a couple choices. You can figure out what the sum of those fractions is using your fraction buttons on your calculator. Depending on what calculator you have, the button may look like this. It might look like A, B, C. There are lots of different types of buttons on your calculator that it might look like. Some calculators just look like this. Okay, so you'll have to figure out what your calculator is like. If you want to learn more about how to use your calculator, you can go to my playlist on my channel, as I have an entire playlist for how to do all these different things on your scientific calculator that you probably never even knew existed or that you could do. Now, if you don't want to do that directly, well, we can look at the greatest common factor. And the greatest common factor would be the multiple of 53 times 11. So what we're going to do here is we are going to multiply this fraction, top and bottom, by 11, and this fraction, top and bottom, by 53. Multiplying top and bottom by the same number is just multiplying by 1. So we're not changing anything, but we're going to create a common denominator by doing this. Because 53 times 11 is 583. So our first fraction will have a denominator of 583. And the second fraction will have a denominator of 583. Our numerators is 1 times 11, so that's 11. And the other one is 1 times 53, so that's 53. And we still have our centimeters here. Always keep your units. All right, so now we can add them because they have the exact same denominator. So 53 plus 11 is just 64 over 583. Now we're not quite done because we haven't solved for the focal length. We've solved for 1 over the focal length. So to solve for the focal length, what we're going to do, you can cross multiply, or we can simply, in math, we say take the reciprocal of both sides, or just flip the fractions. So we can write this as f over 1, which is just f. And the other one will be 583. Now our centimeters are up here, divided by 64. When we pull out our calculator, we get 9.1 centimeters. So there is our focal length. Was that a lot? I get it if it was. Let's try some more examples. In this question, we have a magnifying glass with a focal length of 18 centimeters. So we know that f is 18 centimeters. We're going to be solving for something different this time. And we have to remember, is that positive or negative? So remember, if we go back, positive is for converging lenses. So this is where you have to know that a magnifying glass is a converging lens. Specifically, it's a converging lens where the object is placed within f, inside of f. So this is going to be positive because it's converging. It says a leaf is located 13 centimeters from the lens. So that makes sense. The object is inside of f. So DO is 13 centimeters. It says where will the image of the leaf be located? So we're looking for DI. So let's plug things in. So we got 1 over 18. That equals 1 over 13 plus 1 over DI. So now what we're going to do is I need to isolate for DI. So this term here, we need to bring it to the other side of the equation. And we can do so by subtracting 1 over 13 from both sides of the equation. Okay, if we do that, it'll cancel on this side, and we're left with it on the other side. So we've got minus 1 over 13 centimeters plus 1 over 18 centimeters equals 1 over DI. Now we can do what we did before. So we've got common denominator of 13 times 18. So I'll multiply by 18, top and bottom here, and by 13 for this fraction. That gives us our common denominator of 234. So this fraction is minus 18, and the other fraction is 13 over 234 centimeters. And that equals 1 over DI. So now we have negative 18 plus 13. So that's negative 5 over 234 centimeters, which is 1 over DI. Flip or take the reciprocal of both sides, and we get, I'm just going to continue over here, DI equals 234 over negative 5 centimeters. Put this onto our calculators, and we get negative 46.8 8 centimeters. Here we go. Still having trouble? Let's do one more. So in this one, we have a diverging lens with a focal length of 35 centimeters. But remember, for a diverging lens, the focal length is negative. So we have to be careful there. And it's placed in front of a boat. A virtual image is created 25 centimeters from the lens. So this is for the image, so DI, and it's virtual. So that means it's negative as well. So you have negative 25 centimeters. It says, where is the ship located? So we're looking for the distance to the object now. So let's plug in our information. So we have 1 over negative 35 equals 1 over distance to the object plus 1 over negative 25 centimeters. Now, we can rewrite the fraction. 1 over negative 35 is the same as negative 1 over 35. And here we have a positive and a negative. That creates a negative. So we have negative 1 over 25 centimeters. Now what we want to do is we want to bring this term to the other side of the equation in order to isolate for D0, for DO. Now to do that, we have to add it. Okay, we have to do the opposite operation. So this is a negative, so we need to make it a positive. So we're adding it to both sides of the equation. So we have our negative 1 over 35 plus 1 over 25. Keep forgetting my centimeters. Equals 1 over DO. Okay, let's find that common fraction. So we'll multiply top and bottom here by 25 and top and bottom here by 35 to give us our common denominator. So we have minus 25 over 875 plus 35 over 875 equals 1 over DO. So negative 25 plus 35 is 10 over 875. Forgot my centimeters. Let's put them in here. Is 1 over DO. Take the reciprocal or flip both sides. Go up here again. And we get DO equals to 875 centimeters over 10. And for that, we don't even need our calculator because we just move the decimal place to the left. So we have 87.5 centimeters. There we have it. Not so bad. Let's look at the last equation we use in our optics unit. This one is called the magnification equation. Now don't get confused by the fact that we have two equal signs. That just means that magnification can be equal to HI over HO, but magnification can also be equal to negative DI over DO. Now, we've used DI over DO before in our thin lens equations. So what's HI and HO? These are the heights of the object. So HO is the height of the object, and HI is the height of the object's image, the image. Now, we usually draw it when we do our ray diagrams on a principal axis, and just by convention, we are going to make the heights positive if they're drawn above the principal axis, and negative if they're drawn below the principal axis. And the magnification can also be a negative value. It'll all depend on whether or not the image is upright or inverted. If it's inverted, it's going to be negative. Upright will be positive. So let's try two examples with this. Here we have a model of Einstein 18 centimeters tall. So this is the model. So this is the height of the actual object. It's 18 centimeters. and it's placed in front of a diverging lens. A diverging lens creates virtual images, and we also know that it would be on the same side of the principal axis. So the virtual image HI is going to be 12 centimeters. What's the magnification of the lens? Also, on what side of the lens is the image located? Since it's a diverging lens and we get a virtual image, that you should know that the image will be on the same side as the object. But let's figure out what that magnification is. Our equation is HI over HO, which is 12 centimeters over 18 centimeters. Notice the centimeters cancel. So for magnification, we actually don't have any units. It's just a factor of how much bigger or how much smaller something is. In this case, the answer is 2/3, or if you like it as a decimal, we can have round it to 2 decimals, 0.67. So that number is less than 1, so the image is smaller, which makes sense. We can see that here in the actual values that we were given. Let's do one more example with this. Here we have an upright object is placed 17 centimeters in front of a lens. So this is its position or distance from the lens D. So they're giving us DO. That is 17 centimeters. Then we have an upright. So we have two uprights. So the object and the image are both upright. So we know the magnification is positive and it's telling us it is 2.8 times. Okay, so M is 2.8. Since it's a virtual image and the magnification is making the image larger, we know we're using a converging lens with the object placed inside of F. So it says, where is the image located? So we're looking for DI. And I've already explained what kind of lens this must be. So if we go back to our equations, this is the one we're going to need this time. So let's write that one down. So M equals negative DI over DO. Magnification is 2.8. We have negative DI over 17 centimeters. All right, so what we can do is multiply both sides by 17. When we do that, it helps us to isolate DI because 17 cancels here. So we're left with 17 times 2.8, which is 47.6 centimeters equals negative DI. So we haven't quite solved for DI. We got that negative there. That's okay. Multiply both sides by -1, and the negative just comes over to the other side. So we get negative 47.6 centimeters equals DI. And that makes sense since it is a virtual image. Well, I hope that helped to sort of demystify all of the math that's in our optics unit in science for grade 10. And if you have a test coming up, good luck.